What you see here is aminoguanidine bicarbonate. It may not look like much, but today, we're unlocking its hidden potential to create one of the most formidable classes of nitrogen-based energetics. Tetrazoles. On this channel, we've already made some energetics, for example, picric acid, ETN, and even RDX. Out of them, the ETN was the most interesting and powerful at that scale. We were able to get a couple of interesting detonations, and even performed a can test. To rank all of the energetics that we're going to make, we even created a simple rank list of energetics, and it starts with rank 1, containing the weakest energetics like hexamine dinitrate or tetramine copper complexes. And goes up to rank 4. In that rank, however, there are some real powerful ones. And today we will be opening that kind of obscure and scary zone with the synthesis of tetrazoles. Tetrazoles are a really powerful class of explosives, which you can tell as soon as you see their structure. They have 4 nitrogens in a row in a 5-membered ring, meaning they are quite unstable and can output a lot of energy. Therefore, molecules with that kind of structure just make for a very powerful energetics. So now let's actually do the synthesis of tetrazoles. Okay, so to make tetrazoles, we firstly need a procedure. Luckily, some guy named Engager wrote an absolute banger of a report on tetrazoles back in 2009. The papers contain a ton of information about tetrazoles in general, as well as syntheses of a whole lot of them. So let's just follow what he has done. So the paper starts with an OTC route for making aminoguanidine bicarbonate, which is the precursor needed to synthesize tetrazoles. But since we have a lot of it already, we don't need to go through that hassle, and we can just start at the step when we actually form a tetrazole ring. So let's begin. Firstly, I prepared the apparatus for it, consisting of a 500 milliliter boiling flask. Then the next step is to weigh out 34 grams of the bicarbonate and add it to the flask. You can see that aminoguanidine bicarbonate is this white powder with consistency like to that of flour or baking powder. It was quite fascinating that a compound that is hardly soluble in water and is completely resistant to flames and combustion can be turned into some of the world's most powerful energetics. So anyway, using a funnel, I transferred it all to the flask. To this powder, I then slowly start to add 217 milliliters of 15% nitric acid. Firstly, I added all the necessary water to it, because I will then drip concentrated 68% nitric acid into it. I added in total a bit more than 140 milliliters of water, and then topped it off to 217 milliliters with concentrated nitric acid. The bicarbonate doesn't dissolve at all in just water, but it does form this neat effect. In fact, it makes another interesting effect when stirring is turned on, and it kind of looks like some clouds or a tornado. With acid, it immediately reacts to form aminoguanidine nitrate, and a lot of carbon dioxide gas. This foaming effect is actually quite annoying, as it could overflow the flask if too much acid is added at once. In this reaction, aminoguanidine bicarbonate is reacting with nitric acid in a simple acid-base reaction, forming aminoguanidine nitrate and carbon dioxide gas. So I keep adding the acid until all of it is added. Now I'm left with a semi-transputant solution of aminoguanidine nitrate as well as a lot of undissolved product. So now it is time to move on with synthesis and actually do a proper reaction. So for the next step, I need to prepare another solution, this time a solution of sodium nitrite in water. Sodium nitrite is this slightly yellow and incredibly useful reagent, but is also quite toxic upon ingestion. To make the solution, it's pretty simple, and I only need to take 17 grams of it and dissolve it in 35 ml of water. The resulting solution is highly concentrated, as nitrite is extremely soluble in water. But the dissolution is quite endothermic, so the beaker cools down quite a bit. Now, the next step is to dropwise add this nitrite solution to the aminoguanidine nitrate from before. It should be added really slowly, and I will explain why in just a moment. So, with strong stirring, I slowly start to add the solution into the flask. Gradually, we can see that previously cloudy solution turns clear, and that is indicator of progress. So everything that's left to do now is to continue to add this solution in, and keeping the temperature of the flask between 20 and 30 degrees Celsius. Okay, so now let's explain the reaction and why it needs to be added slowly. So previously we added a bit of excess acid to the bicarbonate, so the formed solution is still pretty acidic from the leftover nitric acid. When we add the nitrite solution, it immediately reacts to form nitrous acid and sodium nitrate. This newly formed acid is highly reactive, and it reacts with aminoguanidine to form an intermediate product, guanyl azide. This reaction is a bit untypical diazotization reaction, and those reactions are usually quite sensitive to heat, but they generate heat when they take place. If nitrite is added too rapidly, some side products could form, and we don't want that. So long story short, the additions were done slowly and with patience, which was pretty hard because who has patience in chemistry? Nonetheless, I wasn't very patient, and I ended to have to cool the solution down with some ice. When I added all of the nitrite, the resulting solution is clear, and it should all pretty much be reacted by now. But to be absolutely sure that it has indeed all reacted, I left it to sit for about 20 minutes. So now we have our intermediate product, guanyl azide. It is actually a very interesting molecule. I mean, it has an azide group and can be actually used to make some very interesting and obscure secondary energetics. If you'd like to see that in some other video, let me know in the comments. Anyway, we now need to cyclize it, and that will form our tetrazole ring. Okay, so now we are only one step before our first tetrazole. We have this transparent clear solution of our diazotized intermediate compound. And I find it very interesting that this solution is actually so close to the final product. In fact, just one step away, but it isn't anywhere near energetic. I took a small sample of the solution and then slowly evaporated the excess water out of it. Then I strongly heated the residue with a flame, and apart from some smoke with horrible smell, nothing really happened. Okay, so now once we're ready, we can cyclize the intermediate. To do that, it's pretty simple. And I only need a chemical called sodium carbonate. It is a rather common reagent in a lab and can be easily made by cooking regular baking soda, which is chemically sodium bicarbonate. Otherwise, it is just another white powder. So now to continue, I start stirring the intermediate solution and then added 29 grams of sodium carbonate in. At the same time, I also start heating the solution to a boil. To one of the flask's necks, I also install a reflux condenser, which will condense water's vapors and prevent them from escaping out. Now, I only need to continue heating and stirring this solution at reflux for approximately 4 hours. In that time, our intermediate should hopefully cyclize and thus form our desired product, the tetrazole, or to be completely accurate, 5-aminotetrazole. But there's one catch with this synthesis. In this specific reaction, the product is 5-aminotetrazole, and even though it has a tetrazole ring, which is extremely energetic, in this case, it is stabilized by that amino group there. So rather than being a powerful energetic, it just burns really vigorously when heated to get an actually powerful and explosive compound. There are a few things that we could do to aminotetrazole to destabilize it and thus make it energetic. The first thing is that we convert it into nitrotetrazole, a class of compounds known for their extreme power, ranking them in the very top of modern energetics. And that is what we will be making today. But there are many other interesting and equally powerful derivatives that can be made from our aminotetrazole. Engager documented them really well in his paper, and we'll try to make some of them. But there is one specific compound, in fact, this one, and it can be converted to infamous, quote-unquote, man's most powerful energetic, isocyanogen tetrazide, or more known as azidoazide. But that is a topic of another video, so don't miss it when it comes out. But okay, let's not get sidetracked and let's return back to the synthesis. Now the mixture has been refluxing for about 4 hours and the reaction should be completed. Now we just need to bring the solution's pH to 4, and upon cooling, our product should crystallize out. When it did, it formed these incredibly beautiful large crystals that were so mesmerizing I almost didn't want to scrape them out. But I removed them really carefully, and they kept their beauty, and that is our product, 5-aminotetrazole. Okay, so now we have our first tetrazole, and of course we need to test its energetic properties. Like I said earlier, it is stabilized by that amino group, but it should show some energetic properties, as it, of course, has a tetrazole ring. So I transferred some to a strip of aluminum foil and heated it with a flame. You can see that it crackles and burns with a really loud crackling flame. Okay, so this was our first ever tetrazole. This specific one is an explosive, but it has quite a few other interesting properties. But now we will make some proper and extremely energetic tetrazoles, so buckle in, because it is going to be extreme. So for our first real explosive tetrazole, I chose to first make aminotetrazole's close relative 5-nitrotetrazole, or more specifically, its sodium salt. The two molecules might look almost identical, as they only differ from 2 oxygens in place of 2 hydrogens. But it is this newly introduced nitro group that transforms a relatively non-energetic compound into one of the most powerful and quite sensitive energetics. Nitrotetrazoles will be also very useful later, as they can form salts and complexes, meaning that they can be functionalized and used in very diverse applications. So now, let's make it. But before we start, I just want to clarify that this video is made for educational and entertainment purposes only. And what will be done can be pretty dangerous if not conducted carefully and with right knowledge. Here it is also done on a relatively small scale, and the end amount is not enough to present a huge danger. This is not a tutorial. Okay, with that out of the way, let's continue. To make the sodium nitrotetrazole, we need to prepare two solutions. Solution A, which contains 5 grams of previously made aminotetrazole, and dissolve it into 25 milliliters of water. To this solution, I then also need to add 3.6 milliliters of 68% nitric acid. The solution B is prepared by dissolving 9 grams of sodium nitrite into 50 milliliters of water. The special and quite terrifying part of this reaction is that it has to be done at 65 degrees Celsius. So to that end, I prepared a water bath, which was heated to around 65 degrees. Into it, I then lowered both solutions and then waited for them to get up to the desired temperature. Once they did, it is time to start adding the solution A to solution B. The order of solutions is very important, and if done incorrectly, it can become dangerous. The moment we added the first drop in, we could see an immediate reaction. It is quite scary knowing that you are synthesizing a very powerful energetic and watch it bubble like that. Anyway, I just kept slowly adding in the rest of the solution while maintaining the right temperature. Okay, so now let's talk a bit about the reaction. Like I said, it is a bit unusual one because it is classified as a diazotization reaction, and those are usually done at low temperatures to avoid decomposing the delicate intermediates. But in this case, we are kind of playing with fire. What it does is that it basically provides enough heat that there is a relatively controlled runaway diazotization reaction, which would usually be really bad, but in this case, it is the way to oxidize the aminotetrazole to nitrotetrazole in decent yields. But we have to be quite careful because we are ultimately forming a very powerful energetic. Okay, so when the additions were finished, I was left with a light brown solution. Pure sodium nitrotetrazole is actually colorless, but coloration is due to some impurities. Now we have today's end product and our first ever actually energetic tetrazole. I was very hyped to try it out as I wanted to do tetrazole chemistry for quite a while. And now the time has finally come. So for the first test, I started small and I decided to first try to heat the crude solution. Along with mostly our nitrotetrazole, it also contains side products like sodium nitrate and leftover aminotetrazole. So I got some onto some aluminum foil and slowly heated it. It started boiling and splashing everywhere, and when it eventually dried up, I expected it to violently explode, but that wasn't the case. Instead, it just smoked off with a slight poof and did almost nothing. Firstly, I didn't know what was wrong, as it should explode, but then I figured that it is likely too wet. So I slowly evaporated some of the solution and got some crystals. They weren't nice and pure, instead they were very dirty, but I hoped that I would get just some energetic response. So I tried again. The same happened. I was a bit concerned that I had failed the procedure and destroyed a lot of my precursor. But then I thought a bit more about it and came to a conclusion that my product is just too crude. I was going to have to do a recrystallization, but I really didn't have the time for it then. Instead, I opted for a quick route that would get me just some results, and that is to dissolve a bit of crude crystals in some acetone. So I tried just that. I dropped a small crystal of my product on some foil and then added a couple of drops of acetone onto it. Then I heated it very slowly. And finally, I got a detonation. It was extremely loud and powerful, and it made a hole in the foil with ease. So I tried again a couple of times, and it always produced at least some kind of detonation. At that time, I was already stunned by how powerful the detonations were. But later, when we will purify the tetrazole, it will get even more powerful and insane. I performed some more of these tests, but now it is time to do the last thing for today, and to actually purify the crude product and get pure crystalline sodium 5-nitrotetrazole. To do that, I recrystallized the crude product from water, and with some difficulties, I managed to get a small amount of very pure sodium nitrotetrazole. Now, you can see that it is not as yellow and it shouldn't contain many impurities. Now we can finally reveal its unique properties, with the first one being the fact that it is now an actual explosive, and it does actually explode vigorously without help of solvents. Despite that, it is really not very sensitive to flame or heat. To actually detonate it requires quite a lot of heat, and it won't detonate from a short exposure to flame or heat like some other energetics. To showcase that, I put a small amount of it onto a cola can, and I will heat it strongly until it detonates. You can see that it doesn't just immediately detonate, but it firstly melts, then starts to decompose a bit, and then finally vigorously explodes. This is the reason why it cannot be used in explosives, as it is just not sensitive enough. But this problem can be very easily solved by simply changing the cation to a heavier metal, such as copper or silver. But this is something for future videos. Now let's try to confine it. I don't think it will make it any better due to the reason I just explained, but let's try it anyway. To do that, I simply put some of it onto a sheet of aluminum foil. Then, I carefully moved all of it into one spot and then twisted the foil to close it and form a small sac full of tetrazole. But now let's quickly try some other things, as this video is already very long, but make sure to subscribe if you like it. Okay, so I tried to do a proper can test, but the sodium salt is just too insensitive and I couldn't get a proper run, so that'll have to wait for another video. Instead, I tried setting of some RDX with it, but that too failed because again, the sodium salt is much less sensitive than RDX, and the latter just ignites before it can get set off by the tetrazole. So let's have one more look at sodium nitrotetrazole detonations for today. It is incredible that a nearly subvisible amount can detonate with such power that it tears the aluminum foil, and that is power of nitrotetrazoles. In the future, we will make a whole lot of them, so don't miss out on those videos when they'll come out. So that is all for this video. I hope you've enjoyed it as much as I did, because I've always wanted to work with tetrazoles. I mean, they are so cool. Like, how can you even put more nitrogens in a ring? Well, I suppose you can, but you get the point. Anyway, that's all. See you in the next video. Bye.